The machine runs and it produces wood, but it's a long way from fully automated. And frankly, it's just a long way from being reliable at all. We're getting these bandsaw blades breaking. We're getting the Z-axis not moving up and down. It's nowhere close to the ability to like repeat and cut again without a human being involved. Well, I definitely fucked up another blade. Got twisted all around here. And it might not be done for, but it's not in the pristine condition anymore. That's for sure. It was running up against that, and that's fine. Didn't look like it was pulling particularly hard in one direction or another, but it might have been. It was just running through this cut, and then clank. Let's see if we can figure out what went wrong. Well, I noticed that the blade had started to move back and forth ever so slightly. And in this case, I can see that there are these sort of micro tears in the blade that are just starting to form. So that blade has taken some plastic deformation all along its leading edge. Now what's interesting is this happened shortly after there was I was cutting a large board. The board was fully cut and then essentially fell on the blade, stopping the blade. So it's a big, thick board. I had it braced in the back, but the front of it sort of falls onto the blade, catches right sort of in the corner there, and that stops the blade cold. Just with the friction, presumably. And I think that does seem to do it. Now the question is, how then you stop the board from like falling onto and catching the blade? It's a very interesting question. And was there anything else that could have caused these microfractures that are now all along the leading edge of that blade? That is the question. Let's take a nice close look at what we've done here, because there's a lot going on. Up here, we've got a new 3D printed saw blade guide, and our reflective sensor is on the back of it. That allows us to say whether the saw blade moves too far forward or is actually in position where it's supposed to be. And if it moves too far forward, then the sensor fails to fire, and the machine notices that something bad is happening. If we move over to this side, we also have a reflective sensor that's attached to this coupler. I've put some metal tape on that. As the wheel goes round and round, that metal tape comes into contact or doesn't come into contact. It's not a coupler actually, but this basically acts as a very primitive encoder, but we don't need to know exact position. We need to know velocity, or rotations really, rotational velocity. And in this case, we can get a very good understanding of the number of rotations by just counting it. And we need each of those to last for a while because this thing's gonna be spinning pretty damn fast. So even in like 100 milliseconds, we're probably gonna get a good number of readings. Next, instead of putting the power directly to our motor, we've wired it instead over to the control board, and the main power cable also goes to the control board. So this wiring comes up here, and now this is what wiring land looks like. Here in electrical land, there's a lot going on. Let's start with the power. So now we've got our 220 volt main cable coming in here and getting fed down to a relay. That relay is itself being controlled by our microcontroller. Now each of these little relays only supports 10 amps each, but they are rated to like 240 volts. I'm hoping that using 2 of them is enough to let the saw run. The saw is only 3,000 watts or so, maybe even a little bit less than that. So it really should be able to run as long as it's spread out a little bit. Plus there might be some wiggle room in those specifications. So the relays allow the computer to turn the saw on and off. That is assuming that the main switch, which is over near the outlet, is actually flipped on. So now in order to run this thing, the computer has to agree it can run in addition to the human flipping the main switch to run it. That's how we can turn the saw blade on and off when there's problems or when we want to move things without the possibility of running into them with the moving blade. Now another major change in here is that we've got the 2 new sensors are wired in. They've got like a bunch of wires coming in through here. These little curly cues are coming in, and they're attached to our control board. I also went out of my way to print and make a little 5-volt distributor and ground distributor for all the things that need to plug into 5 volts and ground. So we are ready from an electrical standpoint to try things. And indeed, I put it into a diagnostic mode just now so that we can observe what's happening. First off, if I move the wheel, we should see the sensor for the saw blade motion come on and off. You know, we give it a little spin, you should see it come on and off and on and off and on and off as that thing spins. So that one appears to be working correctly. The other one is if I move the saw blade into a out of position, it now notices that. I move it back in position, it's looking good. So the sensors appear to be hooked up correctly, and now it's just a matter of taking it out of diagnostic mode and making sure that the software is working correctly. Today I had to replace this blade guide. The blade had actually come up into this little crack right through there. You can see where it was rubbing and fell off of the bearing. It's supposed to be supported by this back bearing, but it wasn't being supported by it because the back bearing itself had started to sink into the plastic and melt. Basically, it was sinking into the plastic because the bearing itself was getting really hot, just rubbing against the plastic and heating up the whole thing. Now it's sitting on top of a washer. So the washer is static against the plastic and the bearing sits on the washer. Not a complicated change, but it makes the difference. I had a false alarm on the speed sensor a couple times. to the point that it wouldn't even run. It just kept happening with this false alarm. If you remember correctly, speed sensor is a little reflector there. I put it into diagnostic mode, and indeed, I could see that it was jittering back and forth between 1 and 0. Didn't know why that was happening. It used to be running perfectly, so very strange. Initially, I thought it was reflections or issues with maybe the surface or something like that. Eventually, I ended up taking the sensor off. Just took this whole post off. Tried sensing against other things, wasn't working correctly. Took it on its side and sensed it against things. Suddenly it was working perfectly. I put it back on and it was working perfectly again. Ran the saw, instantly stops working. And that's what made it obvious. You know, you can see, if you look at this sensor really, really carefully, there are little holes in it. I don't know how well we can even see this. Oh, can I see that? I'm not gonna be able to see it well. There's little tiny holes in that sensor. There's little tiny holes in the back. There's little plates in the front, so the diodes are not fully exposed. And almost certainly sawdust got in there. There must have been a piece of sawdust that was occluding those sensors. It's a very dirty environment that these things operate in. So sawdust occluding the sensor. When I turn it on its side, the sawdust falls away. You know, when I turn it back, maybe the sawdust is still out of position. When I shake the shit out of it, the sawdust falls down to the bottom and occludes the sensor. Swap the sensor out. Put a bunch of glue on it so nothing can get in there. It's a low temperature, like it doesn't generate any heat, so it's, I don't know why they didn't just seal it themselves, but whatever. This is the Z-axis motor. There's one on either side. And I've been having some trouble with my Z-axis not moving in some cases. The more I think about it, that should not be happening. This motor itself is rated at 10 Newton meters, and I have no reason to disbelieve that. Now the thing is, 10 Newton meters is a number you might not be very familiar with. So let's just look at some math on this for a second. The gear that actually interfaces with the racking here is about 15 millimeters in radius from like the center of the spindle. It's really not much. And 10 Newton meters times 1,000 millimeters divided by 15 millimeters should be giving me 666 newtons of force, which is an incredibly large amount of force. That is very, very strong. I remember hearing one time that, well, no, we won't get into it. Anyway, so 666 newtons in pound force is about 150 pounds. Each of these motors should be able to pull 150 pounds up and down. I shouldn't even need a counterweight with how strong these motors are. So the question is, why are they not delivering that? They have the voltage they need. I don't think there's anything wrong with the drive system, like the current and voltage. But you know what they do have? They have a keyway I'm not using. Basically, the couplings that I have here are just friction fit couplings. And that means that, that they will slip if the forces are too great. I intentionally didn't use the keyway, partly out of laziness, but also partly because it's nice to design in a place where things fail gracefully. And that keyway slipping is a very graceful failure. It means that the keyway isn't going to break, the motor's not going to break, the racking's not going to break, it's just going to slip. But I think I'm not getting the power I need until I cut that keyway into both couplings and then make it so that nothing can slip between the motor and the racking. So it's time to do that perfectly. I might even have to do it for all the motors. There it is, finished keyway. Used a broach to cut 1.5 millimeters down on one side. Used the milling machine to cut 1.5 millimeters on the other side. And that's a 3 millimeter wide key. So off we go. I've cut the keyways, but the machine still isn't moving smoothly. It can go, well here, I'm trying to make it go up. You can see it's jogging like that. It can go down at this point, but not up. But watch this. When I make it go up, it starts to move jerkily. A little push, and it moves smoothly. I am just not getting the power out of those motors that I should be getting. There are 3 possible reasons I can think of for why the Z-axis doesn't move up and down. One is that it's wedged. It just takes too much darn work to move the thing. But when I push it with my hand, it moves. So I don't think it's that. One is that the motors themselves are misrated. They are incapable of delivering the power needed. That could be. One is that my motor drivers are incapable of delivering the power needed. For example, maybe they're not getting enough voltage, or maybe they're misrated. None of those is the case, I think. When I literally look at the motor driver, it looks like there's a whole configurable table for how much current it's willing to give. And it looks like the thing is not currently configured to give maximum current. These little switches, switch 1, 2, 3, and 4, those would all be like, what is it? Off, 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 on gives the highest possible power. And it looks like they're off, on, off. So off, on, off. I'm giving this thing like 1 amp of current when I should be giving it 5. So it's not working because I'm not giving it the power that it's asking for. It's pretty stupid of me. But let's fix it now. Okay, First time trying it with full power. Let's see if it can move up this time. Look at that. Under full power. That shit moves totally smoothly. It was fine. I was just not giving it full power. I was giving it 1/5 power instead of full power. It can move up and down just fine. That's embarrassing. Attempt number 3 at a full cut and return. Automatic cut and return attempt number 6. We've got keyways cut on the motors. We've got the motor controllers upgraded to actually run 5 amps instead of 1 amps. That was a silly mistake. There is a new hose connector because I ripped the old one off twice. And now there's actually a metal cage around the drive wheel, both for safety, which I've been meaning to do for a while, and to hold the hose up so that it doesn't get snagged. There's also a limit switch in the back and a limit switch in the front that it can use for positioning in case the dead reckoning doesn't work. The long distance dead reckoning for some reason still not quite right. Yeah, time to run.